We move on with Professor Jennifer Rupp, who is the Thomas Ward Assistant Professor of Electrochemical Materials at the Department of Materials Science and Engineering at MIT. She's also Assistant Professor at the Department of Electrical Engineering and Computer Science. She has a PhD from ETH in Zurich. Before coming to MIT, she was an assistant professor at ETH in Zurich. And Jennifer's research interests are solid-state material design and computing of structure-property relations for novel energy and information devices and operation schemes. She also has received many awards, among them the Displaying Future Award by Merck, Volkswagen Science Award, the Top 40 International Scientists Under the Age of 40 by the World Economic Forum. And Jennifer's talk is titled Lithionics, Next Generation Materials and Operating Principles for Neuromorphic Devices. And we will find the right attachment here, the right adapter.
Okay, all right. I'm still figuring out how to get my talk on.
It will come up.
Okay, that's great. All right, so good morning, everyone. I'm quite excited to talk today here. And here are actually my slides, so that's really nice. So I want to give you actually in the first part kind of like an overview of what memristors can do. And I just want to connect here to Vivian's talk, who was talking about deep neural networks. And I will go one level deeper, asking the questions, what are memristors and what can they actually do as building block when they would be later integrated in a deep neural network. And then I will come in the last part to a new part of our labs research that we have actually, showing you how one can use classic lithium-type battery materials and the ions in that actually to mimic synapses and actually use that for neuromorphic computing. So materials that has been used in batteries could gain additional value and could actually also supply additional functions and just be an energy storage on board. When we think about artificial intelligence, then this can actually enable machines to think and do actually different complicated operations like humans. That's actually quite fascinating, and I just want to show you real quick a technological landscape because we want to discuss through this workshop what is coming up in the next 10 years. So a part of that is actually to look into neural networks and using actually the mimicking of neurons that we know from human cell biology to actually do quite complicated operations when integrated in a chip. And I want to run here real quick this analogy. So when we look actually in a classic neuron, then you have actually here the cell kern, and you have the different dendrites which can actually connect and have a certain synaptic weight, which allows you actually to transfer information. And once the nucleus has actually received all that information goes over a certain threshold, it will actually fire to the next neuron and do a connection. That is actually what's happening right now when you think really hard about understanding that talk. And the ions that are actually fired is actually potassium and calcium ions. The question is how to mimic actually the simple neurons by hardware and what to type actually as different kind of units to do that. And one way to operate is that actually with so to speak memristors, which are very tiny devices of a metal, a transition metal oxide and a metal on top. And if you make those thin enough, then they allow you actually to have a similar ionic transfer on a high local electric field where the synaptic weight would be actually sitting here in the oxide. And if you have several of those interconnected in a crossbar array structure, then you can actually run something similar as an artificial neuron where when you reach a threshold, you have a certain output value that you can use for computation. I'm really showing that. So what would have been before actually the synaptic weight in a biological human neuron would actually be here over there in the dendrites. And we have to think about what are the materials that can actually do that and have actually the synaptic weight analogon in the hardware, for instance in a memristor, and how to actually compose these materials and how do we understand those. And there's a lot of work actually on these memristors looking into memory application. You will find 95% of all the papers. The tricky part is when it comes to neuromorphic computing, there actually the synaptic weight and also the dynamics that you need are very different. So we have to actually really understand that well. So to go one step deeper and actually looking at what is the output curves that we could use later in these different neuromorphic computational operations, then we can see when we look in a classic neuron and we look at the current voltage profile that this is a hysteretic relationship which comes from the ions that are flowing in a certain postsynaptic time retardation. And you can assign actually different resistance state changes that you have over the derivatives that you can later use in the computation of the brain. And we can mimic something similar in a so-called Memristor. So in the Memristor, you have also hysteretic current voltage profile, and that happens because you have very high local electric field strengths that leads, for instance, to formation of filaments or different interface regions of defects in the material. And when you reverse a bias or you change an amplitude, you just like go in the other direction. And this gives you actually what you don't know from the textbook, where we normally talk about ohmic resistors, which would be a linear relationship, but it gives you actually here this hysteretic current voltage profile that is a characteristic time retarded resistance response actually that you can tune over memristors. So how have actually memristors been discovered? So this goes actually back to around the 70s when it was actually found by Leon Schuer that there should be an alternative hysteretic current voltage relationship that should be existing, a so-called memristor. And it came out of like looking into passive circuit elements and understanding that there must be something else instead of having the resistance, the inductance, and all the other elements that you have around. So he actually postulated that there should be such a hysteretic memristive curve, but it took up to 30 years later, or 40 years later, until what was found and postulated by IBM and Hewlett-Packard, that they could actually find when you go small enough in transition metal oxides these memristive processes. Now what's quite fascinating is that actually you can reach a similar density of these memristors on a chip comparable to 10 over 10 per square centimeter what we have actually as synapses in the brain. And both are ionically controlled systems. So what have the ions actually in the brain, like potassium and calcium, are normally in these memristors oxygen ions, copper or silver ions that you find. And both are non-binary response systems that you can use actually in artificial intelligence. So the really hard part as a material scientist is to understand the dynamics, understand the different resistance states, and understand how to manipulate those. And that's actually where I would say the tricky part in the field right now is. So for this workshop, I have kind of like put up here a little bit of what my group's vision and kind of like sorting is of the field right now in memristors. There is two types of memristors that are existent so far. So one is a so-called filamentary memristor, and the second one is a so-called interface memristor. In a filament memristor, you apply a bias to this unit here, and you will actually have an electrode, for instance, like copper, and it can form through an electrolyte a filament of copper connecting to the other side. If that's happening, you will have a very abrupt change in resistance or in conductivity, and you will see actually a very quick onset of the conductance to the other states that you set. However, later this becomes retarded when actually swinging back to the state once you take actually the signal off. And the consequence of that operation on an atomistic scale is actually that you have a very low symmetry for this filament-based memristors. And the second part is that your accuracy is very low, right? But the good news is because you have actually a very fast motion of cations, you have a very fast switch speed, which can be in the nanoseconds. The other part of memristors that have been published actually in literature, and I want to highlight here the work of Young and Strukov and others actually from HP and Rainer Waser over here, where you can read much more about it, is the interface memristor. And in the interface memristor, you can actually have here defects that you accumulate at one interface, and when you apply actually the bias in a reverse direction, they would just shift back to the other side. And you're shuffling back and forth mostly oxygen ions over defects in the electrolyte material. The consequence is that the symmetry is quite high, so you don't have such an abrupt change like in a cation migration mechanism. The accuracy is high, but the speed is relatively low. Okay? So you are in a constant dilemma with memristors. I call it the memristor dilemma. You either have a fast speed but a low symmetry and low accuracy, or you have a low speed and you have a fast symmetry and accuracy in the memristor, depending on what you pick. So what's the impact of that? The impact is later that in image recognition, and that's one part actually of what you want to use these deep neural networks for, as Vivian just pointed out, if you have a pattern, then the ratio between the resistances that you can access and the symmetry will define the synaptic weight. That's what you see here. And that is going to define over a certain time and the dynamics of your ionic movement, how fast and how well you can resolve that image. So this is quite relevant. So what we can learn from that is that we are actually in a non-ideal world, and what can we do now as material scientists to play with that, and in an ideal world actually get the speed up and also accuracy and symmetry up. So the most classic way of what you could do is take, for instance, defects and manipulate the defects either by extrinsic dopants or strain. That has also been done in electronic transistors. There's like various examples. But to be very honest, even though I have also published in those, there's a certain extent in which you can change the resistance values or the dynamics, but you will be limited, for instance, on the resistance modulation, at least by a factor of 10 to 1,000, whatever I can dope in the material classes I showed you before. So there's a certain range I can manipulate, but I can't go beyond that. So to come back to this dilemma, you can either have asymmetric fast switching, or you can have switching in a symmetry, but with slow dynamics. So we need to come up with a third class of new materials on how to solve that. And that is what I hope to show you in the second part of this talk. So there has been some recent ideas actually in the field to move away from those ions that I showed you before, which are either using oxygen, copper, and silver very commonly in this either filamentary or interface-based memristors, but to look, for instance, in ions that could actually migrate much faster. Can we make, for instance, a bipolar interface memristor, but use actually ions that have much faster diffusivity, like lithium? Lithium is a great fellow. It was shown in the last 5 years in the solid-state battery industry that you can actually fabricate very nicely thin films with a high accuracy of lithium. And you have much more options to later vary the symmetry and retention, but keep this interface mechanism, but use actually the fast propagation of the lithium. And also you need a very low energy to move lithium around. So this could actually be a very interesting material to look at. So what has been done, there's a fantastic paper I want to point out from Alec Tallinn from Sandia Labs. So if there's one paper you want to read on this topic this week, read the Alec Tallinn paper. And it reveals that lithium cobalt oxide, which is a classic cathode material in the battery, can be used, for instance, to compute information hysteretically in a memristance. And the interesting part is that you can use the lithium that you pump in and out as a trigger to alter later kind of like synaptic weight of the material. And there has been several other materials like lithium natrium titanate or lithium iron oxide that have been shown to have capabilities to use that actually in neuromorphic computing. Now that is all very nice. However, these materials may not be the most ideal ones because you still need a lot of energy to move lithium and lithium cobalt oxide, and also it's not very environmentally friendly if we think about the cobalt crisis. So what my team proposes is to make the first lithium titanate memristor, and that is a material that is actually using a classic battery anode where you need a very low energy to bring actually the lithium, to use the lithium actually by a valence change to activate the titanium and have actually very fast dynamics here in the metal insulator transition. The other thing that's interesting is that lithium and titanium are readily available, and there's a wide electrochemical way to use that, and it's a so-called zero-strain material. So whatever I do in my memristor, it's never going to change the volume. So it's actually also a component that later is quite nicely manageable in the circuitry. So what we have done is we have processed some lithium titanate thin films, and you can see an example made by pulse laser deposition. So it's a technique where we use a ceramic pellet, we ablate that, we shoot with a laser, we love doing that, and then we bring it down actually in a substrate, and you can create nice thin films. And that is here an according Raman spectra showing that we have the phase. And the really cool thing I'm excited about to show you is that this lithium titanate can actually be used as a memristor. So this is a hysteretic current voltage profile. You can cycle that actually hundreds of times. And the interesting thing is that you can assign actually huge resistance on-off ratios for this lithium 4 titanate material. So it's actually a new material that we could use in that for computation. Now, one thing that we asked ourselves, well, it has a metal insulator transition. That's actually quite nice. So what's really special about the material is if you have the lithium 4 side here, then it's an insulator. And if I push more lithium in the structure, I can come in a semi-metallic conductor. So the basic idea is we use that material as a vehicle to later change a synaptic weight on demand. So we can later choose for that material beyond classic doping how it's going to switch, and we can do that using a phase change in that material. There has been previous modeling work of Martin Besant, with who we collaborate, in batteries actually, showing that one can also use these two phases, for instance, to alter later the dynamics and the electrochemistry of the system. However, this has never been applied to a Memristor problem set. So we had to actually use a trick to even make this very high conductive lithium titanate semi-metallic conducting phase, because normally you cannot just process that so easily. So what we did is we kind of like make a multi-layer in the PLD, pulse laser deposition processing of the phase we want, the lithium titanate, and we add a second phase, which is lithium nitrate, to later process that as a multi-layer. So you can see as a contrast every 30 nanometers, the phase is going to change. And when we anneal that later, we have internal lithiation sources as the lithium nitrate decomposes, and we can create very finely controlled high stoichiometry lithium titanate material, which is normally very difficult to process, because you need to have a really high control level on the lithium to define whether it's insulating or the semi-metallic phase later on. And here comes the result. So to show you just like for the record that we can actually make in the thin film both phases, yes we can. We can see that in the Raman, looking here into lithium oxygen, titanium oxygen bonds. But coming actually cutting to the chase of what I want to say is that this has a huge impact later on the switching. So we can see here's a Memristor response for the low lithiated and the high lithiated phase. So you see the current voltage response. And there's like three things we can learn from that. The first one is that within one material, depending on the lithium that I apply, I can either be asymmetric or symmetric, and I can change the resistance on-off ratio and the dynamics of the material. That's actually quite relevant, because what I showed you in the beginning is that you have not much leverage to design normally materials to have fast dynamics and affect the symmetry and resistance on-off ratio, because doping can help you a little bit, but not so much as I show you to the extent over here. So what we're currently working on is a device where we create now this lithium titanate on the bottom. That's the one Memristor, and it's a 3-terminal device. And what would be the gate in a transistor is on top of it now a lithium conducting electrolyte and lithium foil. And that allows us, like with a micro pump, to pump lithium in and out, and we can thereby on-demand control the synaptic weight of the unit. And that, I think, is some new approaches, actually, that can help us actually to play actively with the synaptic weight and add actually new solutions to this voltage time dilemma. So how does that tie up on a larger perspective? Well, think about that. So we just showed you that we can do neuromorphic computation with some new class of materials based on lithium. For AI. But think about it right now in this cell phone, or for instance, if you have a cell phone on you, you have a battery pack that's quite heavy, you have some sensors on board, and you have later somehow your processor on board. What if later in the chip architecture you could have one thin film electrolyte, right? And depending on the electrodes and the electrochemistry, it could later either process your data neuromorphically, or it could sense with another set of electrodes, or you would actually have your energy on board but be much smaller. That is what I coin as a new field as Lithionics, and I think that's really exciting times to come. So what has been classic battery materials do not need anymore to be classic battery materials. We could really think out wild for what else to use those. And with that, I come to the end. Normally, everybody shows a really serious picture. I'm not good at that. That's how my team looks like. I think when we go in an elevator from, I don't know, level 1 to level 4 or something. And I really want to express here my thanks to the team, and especially also to Juan Carlos, who is actually in the audience, and Moran. So most of the data you have seen stems actually from his work. And Reto, who isn't here, really contributed to the processing anyhow. So thank you very much for your attention.
Questions for Jennifer, sorry.
Yeah. Okay, so I'm wondering, so you present this, so like with these lithium oxidation states, how would they change if you expose them to air or moisture?
Right, that's a very good question. So, I mean, it's a solid state material, so it would not inflame. So what's quite nice is the lithium is captured into structures, so there's no explosion, inflammation risk, etc. So that's quite good. Now there will be, for sure, some slight modulation actually in the Memristor response if you have exposure to humidity. We have We have been, I think, very early on publishing on the role of protons and actually on humidity in the Memristor field for other oxygen conductors. And to tell you the truth, what has been neglected by a lot of chip engineers is that every memristive material I showed you before will have a reaction on humidity. So you can always couple a humidity settling to a memristive function. So it doesn't matter. I think you do it a bit more than the other, but if you go to 10,000 volt per meter field strength, all of them will do it.
More questions?
Yeah.
So the lithium titanates that you have shown look like two-terminal devices, and you show the memristor response. How stable is that?
It is very stable.
How
So
can it be?
why should it not be?
Yeah. Why
Tell me
shouldn't
why not.
lithium redistribute when you remove the voltage?
Why it doesn't move back?
Yeah.
Well, so a similar answer like what would make a bad battery still be a bad battery and not become a better battery, right? So if you apply the potential and you have actually a certain overpotential at the interface, right, then it will maintain in that state, but it's not a driving force to completely have all the lithium ions go back, right? I think it's very similar to other type of cations that we use in this one. There's no driving force for them actually to just, without doing something and reapplying a potential to go in another
Yeah,
state.
the driving force is
Right.
to redistribute non-uniformly,
Mhm.
and when you remove the voltage, the equilibrium is uniform. How can it sustain a profile of lithium in a very high diffusivity material?
I think that it's not very different. So if you think about other materials that switches at nanoseconds, let's take that as an example in oxygen ion conductors like titanium, right? Also here you have locally a very high electric field strength, and the material kind of like stays in that state once you switch it, right? But not all the oxygen ions hop over defects back
That's
into
because
the state.
that material like TiO2 hafnium, they don't conduct oxygen fast.
Right.
But this material conducts lithium fast. And so it should
Yeah, but
redistribute.
They don't. So they somehow don't have the driving force to go back. So also when you look at lithium cobalt oxide, right, which is another example of the tiny groups that I showed you, also in those examples they're very stable on several
That's
days.
because it's three-terminal and they open the circuit.
But, right. No. So I think it's three-terminal, but actually when you look at the two-terminal structure, so they one set actually, they apply the lithium, right? But then they go into the measuring part of the two-terminal memristor on the bottom, and that would also remain in that state. So they are actually staying in that state and not swinging back.
But I don't understand.
So I think you can see that as a problem where you have another diffusivity, right? But somehow in those they don't immediately swing back. They don't. So that's as far as I can show you. So actually going back to the result, right? For all of those, here you can run it actually, and it's a very low scatter for Memristor. So they run actually quite stable over several cycles.
Yeah,
and
that's
they don't
fine.
swing
Like
back.
cycling stability is fine, but when
Right.
you remove the voltage, how can
Right.
it not go back? I don't understand.
I think you have to think about it that it's just some order of magnitude increased conductivity and diffusivity compared to other oxygen ion conductors. But also those would not immediately swing back just because they are bipolar two-terminal device.
Let me suggest that.
Yeah.
Take some more
Yeah.
questions. More questions? Yes.
Could you comment on how scalable are those devices?
That's a good question. To be honest, I have not looked into that right now with the team, so I cannot directly give you some numbers on that question. It's a thin film structure and architecture. Currently we test on 400 nanometer thin films, right? So we haven't scaled it further down, but there's a potential actually for as long as you can keep the stoichiometries in processing well, that you can kind of like keep actually that architectures also at much smaller thicknesses.
More questions?
So at the start of the talk, you mentioned two types of memristors: the filamentary one and these new interface-based ones. And
Right.
some of the materials seemed the same between the two types. So is that
Yes.
something that you can decide at the time of fabrication, or?
That's a very good comment. So some materials, and there has been some data that showed that, so on strontium titanium oxide, for instance, that's an example that can either have a filamentary switching or a bipolar switching. And it's not necessarily by the processing alone, so even if you have made a strontium titanium oxide memristor, depending on the electric field strength and the way with either the pulse frequency you have or your sweep rate, it can either be a bipolar or a filamentary switching. So it's one of those exceptional materials that can have both, so it depends on which range you actually operate it. And there has been some paper of our group where we show that by Kubitschek et al. That there can be dual switching, and there's other group with an AFM tip where they probed that by Rainer Waser's team in Aachen. If you want to read more about that.
More questions?
So I'm going to ask a naive question.
Please,
So this slide right here, you sort of imply that the symmetry is a bad, the asymmetry is a bad thing. And I was trying to understand why is that assumed to be a bad thing on this? Can you explain more? Of
Right.
If you think about computing on top of that, it's not obvious that it's a bad thing. But maybe I'm missing something from it.
No, I think it's not a bad thing. It's just like showing the opportunities that it could either be asymmetric or symmetric depending later on the operation you want to take. And so my point here is actually that currently it's very difficult by materials, you would either end up in the one or the other side, and you can make careful decisions, right, on a hardware level. And what's interesting, I think, on the example of the lithium titanate is that you could later by lithiation in the three-terminal architecture even decide whether you want here or more here. And that's actually, I think, the whole point about it, that if I want to do that in strontium titanium oxide, you can to some extent if you operate it in a different regime. That's also what we published by field strength or by sweep rate or pulse rate, yeah. But we're still within certain limitations. And the point is later, I think, something that Vivian also raised for the deep neural networks to be flexible in the choice of materials we have, and for the algorithms later again, to go either this road or that road, or have materials that can perform in both, and knowing how to operate it. Does that satisfy your question? Yeah. Thank you.
Any more questions? So now that we're talking about new materials, this brings another question we heard earlier from Max about temperature compatibility. He mentioned 400 degrees. Some of these materials are not very friendly to silicon technology. And I wonder, for example, lithium can move around quite readily. Is this a problem? How can we handle it? Can you confine it in place so that it stays in your device and doesn't spread anywhere? What are your thoughts on this?
That's a very good comment. So obviously there's some materials that are more easy to handle than others, if you look on the list. So on the lithium, so the processing steps that I showed you that we just published on controlling the lithium level very well in thin films, that can be carried out between 300 and 500 degrees C. So it is, let's say, at the higher end of CMOS compatibility. It is. You have always to be careful, I think, with silicon and lithium. So you will need to have a buffer layer, or like a barrier. I think that's quite realistic. However, that's something that industry knows how to solve if we think about the microbattery industry. So for some zones, this is not a problem to process that. You would have to have a special foundry at the end, right, that makes this one part.
Okay.
Yeah, I think that's realistic to say. But I think it's not a showstopper necessarily for going into lithium. Potentially, you can really use that you have this extra ability for pumping and the fast diffusivity in solid state matter. Or metal insulated transition.
Thank you, Jennifer.
Yeah.
We will.
Thank you.